have a question period at the end, and we will. And we will definitely ask Professor Englert about the theory and everything. So our next speaker is Professor Kibble from Imperial College London.
Well, I'm very pleased to have this opportunity to tell you about this particular piece of work. We had a very fine presentation from François Englert, which mentioned his work with Robert Brout, and also told you something about Peter Higgs' work, which unfortunately Peter can't be here to tell you himself. My job is to really fill in the background to the third paper, which is, there were three papers, of course, published in Israel Letters in the autumn of 1964. This is the third one. The third one was written at Imperial College, and what I want to do is to tell you something about physics at Imperial College in the early 60s. And my two colleagues, Guralnik and Hagen, will tell you more about the paper itself. The group at Imperial College was set up, the theoretical physics group, in 1956 by Abdus Salam. A few of you may have been at the plenary session, the joint plenary session on Saturday, when we had a very interesting presentation from Shirley Malcolm about diversity, in which she quoted from Abdus Salam. I've always thought it was a piece of very good, very great fortune that I was able to join this group in 1959, just 3 years after I just set it up. It was a very exciting time in physics, and this was a wonderful place to be. We had, it was a very, very lively group. We had huge numbers of visitors coming through all the time. In the first year or so, a number of visits from Murray Gell-Mann, Tim Johnson, Stanley Mandelstam, Stephen Weinberg, and many others. This was a time, of course, when field theory was rather out of fashion. The big thing was S-matrix theory, particularly, of course, on the west coast of the United States. We were not by any means immune from S-matrix theory, but Imperial College was one of the places where field theory was still very actively pursued. There were others, of course. Abdus Salam was very interested from the earliest in the idea of unification of interactions. He had a definite goal to try to unify the different kinds of interactions. And he certainly believed from an early date that the answer lay in gauge theories. Yang and Mills, of course, had developed their theory in 1954, the first gauge theory beyond electromagnetism. And interestingly, it was the same theory was actually proposed by a student of Salam's, Ronald Shaw, although it was never published except as a Cambridge University PhD thesis. Yang-Mills theory was really intended as a theory of strong interactions. It was a gauge theory of isospin. But of course, a theory with a coupling constant of order 1 was something nobody knew how to deal with. And so, even although there was this theory, nobody could really tell you whether it was a good theory of strong interactions or not. And for that reason, partly, weak interactions became a more interesting possibility. The idea of a gauge theory of weak interactions was particularly attractive once, oh sorry, I've gone the wrong way. Once it had been established that the Fermi interactions were V minus A rather than S, T, and P, that is to say, they proceeded through the interaction of vector and axial vector currents, and not scalar, tensor, and pseudoscalar. And that strongly suggested that they proceeded via intermediate vector bosons of some kind, a proposal that was made by Sudarshan and Marshak independently by Feynman and Gallman. And right from a very early stage, Salam, as I said, was interested in the idea of a unified theory of weak electromagnetic interactions. Because if you have gauge bosons, these different kinds, maybe you could put them together. His first attempt, I think, dates from about 1958. His long-term collaborator, John Ward, and there were many other attempts. These, of course, his early attempts were not at all successful, but he was trying very hard, and in the end, got there. There were two big problems in the way of electroweak unification, obvious problems: parity and the masses, the bosons. How can you combine, how can you have a symmetry between photons, which are massless, and intermediate vector bosons, W's, which must have a large mass in order to get the weak interactions having weak strength and short range. And the other problem is the parity non-conservation. Well, parity non-conservation and the masses were both obvious distinctions between the two. So clearly, the symmetry between, I don't know why a gamma has become a C, but you must interpret that C as a gamma. The symmetry between the photon and the W must be broken in some way, and it was rather natural to think perhaps it could be broken spontaneously. But that then ran into another problem, apparently ran into another problem, the Goldstone theorem. The Goldstone theorem suggested, or stated, that the spontaneous breaking of a continuous symmetry in a relativistic theory would always give massless Hammond-Goldstone bosons. It was, of course, known that in a non-relativistic theory, like superconductivity, one could get around this. But as far as the relativistic theory was concerned, there was a proof of this theorem which was given by Goldstone, Salam, and Weinberg. It was actually written, I believe, when Stephen Weinberg was on sabbatical at Imperial College in 1962. And this seemed to most field theorists to be a removable obstacle. It seemed to suggest that there was no way of making a relativistic theory that could avoid the Goldstone theorem, and therefore avoid having unobservable massless particles predicted. Now, because of all these things, because there's been all this discussion of electroweak symmetry breaking, I was very interested in 1964 when Jerry Guralnik arrived to spend a year at Imperial College, to find that he had been working on the problem of masses for vector bosons.